Hello everyone. In the last video we talked about Riemann sums and trapezoidal sums and how those can be used to approximate an area under a curve. And in this video we're going to talk about a mathematical tool known as the definite integral, which is something that can be used to calculate the exact area under that curve. Now the problem with Riemann sums and trapezoidal sums is we needed to basically create an infinite amount of partitions or an infinite amount of subintervals in order to get an exact area. And that's pretty much what an integral does. It is represented by a limit mathematically. If you want to talk about what that limit is, we discussed it a little bit in class, but you can always stop by during tutorial and we can talk about it a little bit more. But anyway, for right now, all you got to do is recognize that this symbol right here is a definite integral. And this means take the area under the curve of f of x between what are called the limits of integration, a and b. As you'll notice, a is the leftmost limit of integration, b is the rightmost. We can actually switch those limits of integration if we want to, and that's a property we'll talk about later in this video. But basically all you got to understand right now is what this symbol right here means, and it means that it is the area under the curve of f of x between x equals a and x equals b. So another way to say this is also the integral over the domain x equals a to x equals b of f of x is equal to that area under the curve between that domain as well. So you'll hear that this terminology can kind of be used interchangeably. I can either say what is the integral of f of x over these two limits of integration, or what is the area under the curve of f of x between these two x values. Those two terms mean the exact same thing, and they both mean the definite integral of f of x between x equals a and x equals b. Integrals have a couple cool properties. Just because they represent area, we can add area or subtract area. So what you see in this slide right here is that I've color-coded all these things. We have the red shaded region, green, and the blue dots. The red and the green represent basically two, you could call them subintervals of area under the curve between A and C, in that we have the area between A and B, and then the area between B and C. If we add both of those together, we get this blue dotted area, or the area over the entire thing. Likewise, if we start with the area from A to C and subtract the area from B to C, we're just left with the area from A to B. And that's what these two equations right here basically show. They show how we can use the definite integral and that symbol in order to represent what these areas are. So pretty simple. You can just add and subtract them just as you could add and subtract any other numbers. So the next property about integrals is that if the area under the curve is above the x-axis, it's called positive area. So therefore the area of the section A would be positive 3. And if the area is below the x-axis, that area is going to be negative. So this area would actually be negative 4. So if we added these two together, we would have 3 minus 4, and so this would equal negative 1 if we were to calculate that integral. Now, another way to say this, can anyone think about that? Pause the video and see if you can rewrite these two integrals as one integral. What would it be? All right, well, if you came up with it, we could have also represented this as the integral from A to C of f of x dx, and that also would have been equal to negative 1. Again, that goes back to that property of adding and subtracting areas under the curve that we talked about in the previous slide. So, also, this is what I was talking about before. If we swap our limits of integration, so instead of integrating from x equals a to x equals b, if we instead integrate from b to a, all that happens is this negative sign gets put in front of the integral. So basically, if you're taking an integral moving towards the right along the x-axis, it's just normal. Area above the x-axis is positive, area below the x-axis is negative. But if you integrate in the opposite direction, going from right to left, those flip-flop. The area above the curve becomes negative, the area below the curve becomes positive. I think that's a little bit too much to memorize right there. I think it's just easier to say, hey, pop that negative sign in front of something if you have limits of integration that are switched like this, whereas they move right to left instead of left to right. Another property that we have is called the addition subtraction by the sum rule. So if we have the integral of some function plus or minus the integral of another function, we can just split that up into two integrals. This works exactly the same as taking derivatives. And the reason why is because, as I said earlier in this video, an integral is a limit. A derivative is also a limit, and this is a property of limits. This was that sum difference rule that we get from limits. So you can apply this to anything related to limits, which is why we can apply it to integrals or derivatives. And finally, just like with derivatives, just like with limits, if we have a constant inside our integral right here, we can just pull that constant to the outside. You can always pull constants to the outside, just like how we did with derivatives. So those are a couple pretty simple properties of integrals that are going to be important in this next unit, but really properties that you're just going to be expected to know as we go moving forward throughout the rest of the class. Because we know that an integral represents an exact area under the curve, if these curves form geometric shapes that we can calculate the exact area of, we can evaluate integrals in this way. So look at this right here. We got f of x is equal to 4, and I want to find the area under that curve between 1 and 3. So pause the video, see if you can figure it out. All right, well, hopefully you should have seen that this is just the area of a square. So this just would have been the base, 3 minus 1, times the height, 4, which would have given us an area of 8. 2 times 4 is 8, okay? So what this tells you also is that from now on out, if we have an integral, let's say an integral from a to b of a constant, or sorry, there should be an f of x in there. I meant to write dx. I apologize. So if we have an integral of a constant like this, that is always just going to be equal to what? See if you can figure it out from what we just did in solving that problem. All right, if you gave it a shot, hopefully you came up with, if we just multiply that constant times that space b minus a, we're going to end up getting what that integral is. That's exactly what we had right here. B minus a was this, and here was the constant. So now you guys can evaluate integrals of constants. You know one type of function to do that for. All right, so also, let's pretend we have something like f of x equals 2x. Now, if I want to find the area under the curve between 1 and 2, see if you can do that. All right, well, if you gave this one a shot, hopefully you can see that I broke this up into two geometric shapes, a square and a triangle. You also could have broken it up into a trapezoid if you wanted to do that. But now, so you can see that this approach, either breaking something up into a trapezoid or a square and a triangle, can work for any linear function. So now, if you guys see a linear function, you should be able to know how to evaluate that by just drawing the geometric shapes, okay? So if we go ahead and do this, we would get that area of the green section would be base 1 times height 2. The area of the red section would be 1/2 base, which is 1, times the height, which is 2. So this would end up giving us just 3. All right, so yeah, pretty simple. But like I said, now if you see a linear function or a constant, just by noticing that as a geometric shape, you will actually be able to evaluate an integral. Okay. Now another way we could have done this is with the constant multiplier rule. We could have said this integral was basically the same as 2 times the integral of 1 to 2 of x dx. We could have done that, and therefore our shape would have just been, well, it would have been another trapezoid or a triangle and a square, but it would have just been another shape that we could have used for that. So yeah, we'll learn a bit more exact ways to calculate integrals of functions. We'll learn rules like the power rule backwards and the chain rule backwards and the product rule backwards and all this stuff. We're going to get into that in the next couple of units. Right now, we just want to focus on thinking about integrals as areas under curves.